Okay, so this is our first first lesson in calculus here. We're working out of unit 9 and 10 here, and we're going to take a look at some material out of boxes A, which deals with rates of change, and box B, which deals with what's called the tangent problem. And I thought I'd start us off with an example here. So we've got a situation. A pebble is dropped from a cliff with a height of 80 meters. That's the height of the cliff. And after t seconds, it is s meters above the ground, where they give us a function here that tells us the relationship between the height above the ground, s, as a function of t. So s as a function of t is 80 minus 5t squared. And I've put a graph down here just to show you what the situation is looks like. We've got t down here on the x-axis and s as a function of t up on the y-axis here. And the first question we're asked is to find the average velocity of the pebble between 2 points, between the point t equals 1 and the point t equals 3. So let's just locate those points on our graph to start with here. T equals 3 is going to be over here, so we're looking at this point right here. And t equals 1 is going to be down here, so we're looking at that point right there on our graph. Okay. And we want the average velocity between these 2 points. So you've probably done this kind of question a bunch of times before. Okay? How can we calculate average velocity? Well, what is velocity here? Yep. Or even simpler, yeah, it's going to be the change in position and the change in time. Okay? Or position 2 minus position 1 over time 2 minus time 1. Okay? So we can figure out our positions and our times. So we're given 2 times here, so the denominator is pretty easy here. Our time 2 is just going to be 3, time 1 is just going to be 1. And to work out our positions, we just need to use the function that we're given. So this is going to be our function evaluated at 3 minus our function evaluated at 1. Okay? And we can work out what this is going to be. So we don't need to go through details here. We can just, if we sub those numbers into the function, we get that s at 3 is 35. S at 1 is 75. And of course, 3 minus 1 is just 2. So we work all this out, and we get that the average velocity is minus 20, and that would be in meters per second. Okay. Now, what I'm more interested in here is, what is this calculation that we've done, how does that relate to the graph that I drew over here? In doing this calculation, what have we calculated on our graph? A point-to-point line. So it's like what we've done is we've drawn a line from this point to this point, and what have we calculated about this line? The slope of this line. So what do we call a line that goes from 2 different points on a curve? Anybody remember? This is called a secant line. Okay, so a straight line that connects 2 different points on a curve is just called a secant. So what we've calculated here is we've calculated the slope of that secant line. So this is sort of the first sort of conclusion from this, is that the average rate of change is the slope of the secant. Between 2 points. Okay. Fair enough. So that's our average rate of change. Now, next up, we want to estimate the instantaneous velocity, or the instantaneous rate of change at a particular time. And we're told the time here is t equals 1. So you remember doing this from advanced functions. And the idea was that you had this point, t equals 1. You wanted to find the instantaneous velocity. So what you did was you said, okay, I can find the slope of the secant between that point and some other point. And I would choose different points that moved closer and closer to that original point, t1. So if I've got my green line here, which is my secant, I would take the end of this secant and I would gradually move this point closer and closer and closer along this curve to closer and closer to t1. And I'd calculate the slope of that secant each step along the way. And what I was looking for was I was looking for a value of the slope of that secant that, that everything was sort of heading towards. So that's what we're going to do in this table here. Okay? So I've set up this table, T1, T2. We're going to keep T1 the same. It's always going to be at T equals 1. And we're going to gradually move T2 closer and closer to T1. So we might start something like 1.2, and then move it closer, 1.1, then move it a lot closer, 1.01, and so on. And as we do this, the change in time gets smaller and smaller. So it starts at 0.2, then it goes to 0.1, then we make it small, 0.01, and so on and so on. And in this last column, this is where we're calculating the slope of the secant, just like we did on the previous page. We're evaluating the function at t1 and t2, and then we're dividing it by that time interval. So we can go through the details of this calculation here. S at t1, or the position at time 1, is going to stay the same, so it's going to be 75 every time. And what is going to change is the position at time 2. It's going to start at 72.8, and it's going to gradually move closer and closer to that 75. So 73.95 and 74.89, something, something, something. Okay? But what we're really interested in is what goes on when we calculate the slope of this secant. So for our first row here, we get negative 11. We do it in the second interval where our time, where our delta t is 0.1. We get negative 10.5. When our time interval is much smaller, 0.01, we get negative 10.05. Now, when we look at those values for the slope of the secant, what number are they sort of heading towards? Yeah, they're tending towards a negative 10. So what we can say here is that as delta t tends to 0, okay, because we're making that smaller and smaller, or as t2 tends to t1, okay, as we move those things closer together, the slope of the secant and let's just use that arrow for tends to negative 10. Okay. And to double check that to double check that this was consistent, we also took some points that were on, we did the same sort of thing approaching T1 from the other side. So we took our secant here and we kind of flipped it over like this, and we moved this T2 kind of towards T1 this way. And we did the same sort of thing. So we kept T1 exactly the same, 1, 1, 1, and we chose some values of T2 that were smaller than T1. So 0.8, 0.9, 0.99. Again, we're making this value of delta t extremely small. So it starts at negative 0.2, goes to negative 0.1, goes to negative 0.01. And again, we looked at what happened when we calculated the slope of our secant. So the slope of our secant goes from negative 9 to negative 9.5 to negative 9.95. And what sort of trend do we see in these slopes? What is it heading towards? Negative 10 again. Okay, so we have consistency here. It's heading towards the same value whether we go from the right-hand side of t1 or from the left-hand side. So as delta t tends to 0, or t2 tends to t1 from the left this side, from the left, okay, the slope of the secant tends to -10 as well. So when we saw this behavior, okay, the slopes tended towards the same value from both sides, we would use -10 as the value for our instantaneous rate of change. So we can say, let's see, instantaneous, well, let's try to spell this correctly here. The instantaneous rate of change at t equals 1 is -10 meters per second. There's another way we can express this, okay? And this is what this is all sort of building up towards. When we see these values of the slope tending towards a specific value, whether we go from the left side or from the right side, we can say that this value, -10, represents the limit of the slope, okay? So we can write something like this. The limit, okay, as delta t tends to 0, okay, as we make that change in time, or that time difference, smaller and smaller, of delta s over delta t, or our change in position over a change in time, is equal to -10, okay? So let's just say we can express this as a limit. So express this as a limit. Okay, so this is the limit as delta t tends to 0, is how you would read that. Okay. So the instantaneous rate of change is represented by a limit that we get as we move these 2 points closer and closer together. Okay, does this make sense? Okay, we're okay with this idea of a limit. Now, what does this look like graphically? Well, as we move, a secant is a line that connects 2 points on our curve. As we move these things closer and closer, what we're heading towards is a line that doesn't hit the curve at 2 points, but only intersects this curve at a single point. And we call that curve that only intersects at a single point and is sort of, looks like that, we call this a tangent curve. Okay, so this is the tangent to our curve. So what does that mean? Well, it means that if our average rate of change was represented by the slope of the secant, instantaneous rate of change is represented by the slope of the tangent. Instantaneous rate of change equals slope of the tangent. And we could find our instantaneous rate of change by taking this limit of the slopes of the secant. So the instantaneous range, so the slope, to get the slope of the tangent, what we're doing is we're taking the limit of the slopes of our secant. Okay, so we're going to use limits to find the slopes of tangents. Okay. Use limits to find slopes of tangents.